Hello everyone, we are TeamQubit. We chose piloting quantum simulation of PFAS molecules with PFOS fragments. The motivation behind choosing this problem statement is PFOS and PFOA are called forever chemicals. Due to their strong CF bonds, they do not naturally degrade in the environment, which causes cancer in human beings, harm to aquatic life, and water pollution. Even though these are banned, many companies come up with a lot of variants. Now there are 400 of them, which are very hard to mitigate. So the approach that we have taken is to calculate the dissociation energy for CF bonds on various scales, benchmark results to DFT, and outline scalability to full PFAS.
But convenient for us, though, this problem is very well suited for a quantum computing approach because of how classical algorithms tend to struggle with modeling the highly correlated electrons that are found in fluorine-rich molecules to model their different interactions to begin to figure out how they might break down. And so because of that, algorithms such as the variational quantum eigensolver would be a lot better suited in proving feasible to be used for the full-on PFAS molecules because they directly capture entangled electron states. So knowing this, we then set up a to-do list. We optimized all the geometries to find the active states to focus on using the bonding and anti-bonding orbitals, and then constructed the Hamiltonian, mapped the qubits, and we ran it using IBM's graciously provided API keys. And then we went ahead and chose 4 different molecule fragments to get started on to be able to see how it might scale as they get more and more complex. Complex in the amount of electrons, the number of fluorine in each, and then just knowing how they might scale as they get more and more infeasible to be ran with classical approaches, and to be able to find the most intuition for how these relationships should look, we had a plethora of different classical approaches to then compare to our quantum approaches. And here is what we found. So with the most simple, looks pretty spot on. Everyone's kind of in agreement here. And then with the next one, not so much. The DFT, one of the DFT algorithms didn't even converge and didn't even really have a real output. But we then see here that on this one, the Harty-Falk approach is showing a good example of why it's not known to be as accurate as DFT, but it did run really fast. But we can see here that all of the different VQE relationships model what one would, seeing all of these different classical algorithms, what the more correct ones look like in terms of what were in the most agreement. And so we can even see for the biggest one, which we've dubbed our motif, we have computed this behemoth of a fragment. And these are all normalized potential energy curves to see the relationships a lot better. And so now being able to see that this is proving scalable and able to be used to scale up to a PFAS eventually.
Moving towards PFAS, we know that communities need safer water and soil, which are free from carcinogenic forever chemicals. Strong CF bonds present us with a huge pain point, as they're extremely resistant to natural degradation. And our existing simulation capabilities are a big limitation due to the size and complexity of fluorinated molecules. But now, with the help of quantum simulations, we can showcase quantum computing's role in advancing sustainability and supporting regulators, scientists, and innovators alike. Coming to the roadmap, we started off with simple molecules like H2, CH3F, and CF. Moved on to slightly more complex molecules like CF4 and C2F6, which had a lot more electrons, then finally concluding at the motif. Now, how did our project line up with the quantum for good motivation? Our efforts were directly in line to demonstrate how quantum technologies align with United Nations Sustainable Development Goals, specifically SDG 6 of clean water, SDG 9 of sustainable industry, and SDG 12 of responsible consumption. We are able to showcase that our efforts directly support cleaner water systems, public health protection, and environmental sustainability.
Alright, moving on to the technical impact of our project, we were able to demonstrate the feasibility of quantum algorithms such as VQE, simple VQE, on realistic PFS molecules. Basically, this proves that quantum computing is a very good solution to go in future to break down complex molecules such as motors and etc. And yeah, this has a very big future scope in the field of chemistry. Well, this might be the end of our presentation, but our team qubits were able to also work a little bit on track 2, which is an optimization problem for using quantum computing. So our problem statement over here is traffic signal optimization. Why for why? So basically, first environmental impact. We want to target SDG 13 so that the environmental impact of idle cars, which emit CO2 and pollutants, and also waste a lot of electrical energy, is reduced. Secondly, we want to go towards SDG 9, which is making an industry towards industrial innovation and infrastructure by taking on dynamic challenges of traffic congestion. And thirdly, target SDG 13, which is for urban congestion, which is basically wasting again a lot of time, hours of sitting idle in the car, which again results into a lot of pollution, right? So you might be thinking, classical problems like shortest path already gives us a solution. Well, the classical problems are good when it comes to one lane, right? Because it's a very small area. But when it comes to a city or a country, in real time, it's not at all a feasible thing. Well, before going to that, we're going to use a max-fit algorithm, which is a dynamic programming algorithm that determines the amount of sets in amount of nodes in 2 different sets in a given graph, right? So partitioning the graph nodes into 2 different sets such that each set has the maximum number of nodes. In our case, we're going to model it as follows. Having traffic lights as the nodes, which are the intersection in our graph, well, with the roads being the edges, with the ways being the congestion overall, right? Our traffic is going to be divided into 2 sets. One set is going to be the green light set, which basically states the traffic moving in one way, that's traffic flowing. And the second set is going to be the red light set, basically the traffic halting at that point. Now, doing our max-fit using some quantum computing algorithm, we're able to solve this, deciding which signals to turn green versus which to turn red, such that the maximum traffic volume moves without any gridlock and with as fast as possible, essentially. Right, so how did we test our algorithm? We used an Australian traffic data for 1st September 2025 till 9th September 2025 for our current data, which consists of so many records. It's a big number. Right. And a quantum computing algorithm gave us a beautiful graph which shows green and red lights. But this doesn't really look that nice, right? Let's see what it actually tells us. Well. Key insights from this entire graph shows us that the optimization before, the traffic optimization before and after our algorithm is actually significantly higher. As you can see, during the peak hours, the time is getting like massively saved. And a lot of the other factors like the performance dashboard, etc. Right? Now let's compare our quantum computing algorithm to the classical algorithms, which are like a brute force algorithm or a greedy approach. When we run the algorithms against each other on a local computer, our algorithm is able to outdo the classical algorithms. Well, you can see only 6 intervals because, well, my MacBook can't handle more than that. I'm sorry. Because the data is very huge. Can't complain. But then when we use the IBM cloud, we can see that there's a difference in the output values. Here the classical is kind of outperforming the quantum computing both in time and the values. But let's go back to the fundamentals of what quantum computing stands for. Quantum computing is essentially a probabilistic state, which means that it is a matrix that represents the probability distribution graph for a particular set of outcomes. And it gives the most optimal solution for that given time. Yes, at this stage, our classical methods are outperforming the quantum. But in real time, when the data is live and we need immediate results on a city-wide scale, not on a lane-wide scale, yeah. And this is like a static thing. In a dynamic environment, the classical algorithms are just gonna crash out and in a day it's gonna start smoking up. But over here, it's gonna go on and it's going to continuously give you the most optimal results. So that is the future scope of quantum computing in terms of traffic congestion, to go from this particular state to a very smooth and fast city, and quanta is the future. So yeah, with that, Qubit checks out, and thank you USC, UMD, QEE, and IBM for this opportunity to present and work on these wonderful projects.